Hey, and welcome to the podcast. We're here to talk about kinetics. Kinetics is all about how fast a chemical reaction goes. So what we need to consider is what kinds of things are going to make a reaction go faster or slower. How can we mathematically calculate that? And then start to give some thought about how do we model that kind of thing? How do we measure rates of reactions? So these are the things you ought to be able to do. Kinetics is based on the idea that two particles have to collide in order to react. Not only do they have to collide the correct way, they also must be oriented in the correct way. So even though some things actually collide a lot, they hardly ever react. Why is this? Because they have to collide with the right amount of energy at precisely the right amount of time and in the correct orientation. In other words, we have to have an activation energy that must be overcome in order for a reaction to occur. So let's go visit a pizzeria. Let's draw a person. Here you are. This person's happy. Why is that person happy? Because that person's going to get some pizza. What do we need for this person to get some pizza? Well, how about some pizza? Make it some pepperoni. Draw some pizza over here. Maybe make some healthy pizza, some green pizza. Now, in order for this person to be able to eat a piece of pizza, the piece of pizza has to hit him. That's a really big piece of pizza. Hang on. Let's make the person big enough to eat the piece of pizza. So in order for this person to eat this piece of pizza, the piece of pizza must collide with the person, and it must collide in the right orientation. So let's turn that sucker around. So here comes the piece of pizza. If the pizza sticks in his ear, that's not eating pizza. If the piece of pizza turns around and hits him on top of the head, that's not eating pizza. And if the pizza hits him in the armpit, well, that's stinky pizza. So we want that piece of pizza to be able to spin around and hit him in the mouth. And then and only then can we call that eating pizza. Now, the other thing that happens is when this piece of pizza starts to get close to this guy or girl, let's fix that issue. When this piece of pizza hits this person, as it starts to come close, the electrons in the pizza and the electrons in the person start to go, no, get away. So the problem is, if the pizza just casually approaches with a very slow speed, as it starts to get close to the person, those electron repulsions will push the pizza away. So how do we cure that problem? We just get the piece of pizza sailing through the air fast enough that it can overcome those electron repulsions. So we needed to hit with enough energy to overcome those repulsions, and we need to hit in the right orientation. So when we talk about a rate of reaction, we need to measure either how much product gets made per unit of time, or we need to measure how much reactant goes away per unit of time. So we say how much of a reactant or product, doesn't really matter, at time 2 minus how much did we originally start with at time 1 over T2 minus T1. And why does this look so familiar? Because this equation is the slope equation. Change in y over change in x. So we can graphically analyze this as well. But if we just measure how much product gets made or how much reactant goes away, we can figure out a reaction rate. So for example, we've got no turning into no and O. For every NO2 that gets used up, we're going to produce 1 NO. And for every 1 NO2 that gets used up, we'll produce half NO2. So a problem of when 3 moles of NO2 disappears, how much O2 appears from the balanced equation up here, the answer is 1.5. This graph just shows the changes in concentration over time. So the y-axis is molarity, the x-axis is time, and notice that these are not straight lines. The reaction is going to get slower and slower as the reactant is used up. Less reactant means a slower reaction. So this is not a linear relationship. But we can take the slope at any one point in time, and that's what this green triangle is doing, is at a time of 100 seconds. It's measuring the slope at that line, and the slope at that line will tell us the speed, the change in concentration over the change in time. Notice, however, that the NO is going up as twice as fast as the O2. And why is that? Because look at the balanced equation. For every 2 NOs, you're only making 1 O2. So the NO should go up faster than the rate of O2. Now, where did this graph come from? The graph came from this table right here. All you're seeing is concentrations at a given point for each reactant and product and time. And then they constructed a graph. The things that affect rate of reaction, temperature, obviously. There's something called a Q10, which says that for every 10 degrees increase, about, the rate of the reaction will double. And this is because faster molecules, they collide more, and they collide with enough energy to overcome that activation energy. If you increase reactants, obviously more reactants means more collision. A catalyst, you probably learned of those as being enzymes, will speed up a reaction by lowering the amount of activation energy. And when we say nature of reactants, SA means surface area. If you want to burn a log, throw it in the fireplace, and it will burn slowly over time. If you want a log to burn all at one time, what do? You grind it up into very, very fine dust. We call that sawdust, and you burn it all at once. Mathematically, we can write a rate law. Rate laws always start with rate is equal to, K is just a constant, and that constant stays the same unless you change the temperature, times the concentration of the reactants. If you have 4 reactants, you'd write down 4 things up here. Our equation, we only have 1 reactant, so I'll only put 1 of them. And it's always raised to some power. Now that power could be 0, could be 1, could be 2. In the real world, it could be 1.3 or 1.4, 2.7. But we can only find that exponent experimentally, and we can only find the rate constant experimentally. So how do we find those values of K? How do we find the exponent? We use a method of initial rates. If we just do the initial rate, meaning right when it begins, then we don't have to worry about a reverse reaction turning some of the products back into reactants. That just makes the math way harder, and no one likes hard math. We will just run the experiment using several different conditions. So let's see what that looks like. Here's a reaction. We've got 2 reactants, NH4 and NO2. Let's write the rate law for this. Rate laws always start with the word rate. Then comes the rate constant. Then comes the reactants. NH4, the concentration of it, and the concentration of the other reactant, NO2. And then the tricky part is each one of those has to be raised to some power. We don't know what that one is, and we don't know what that one is. So it's our job to use this data to do that. We can only figure out one of the reactants at the time. So what I want you to do is, let's figure out this one over here, the NO2. For us to figure out the NO2, we need to find an experiment where the concentration of NH4 just didn't matter. So find 2 experiments where the concentration of NH4 didn't change at all. You were right. Experiments 1 and 2, the concentration of NH4 didn't change at all. So let's go look what happened to the NO2. The NO2 from experiment 1 to 2 doubled. All right, so far, whatever happened to the concentration, it had some effect on the rate. Let's draw this out. If the concentration of NO2 doubled, That means the concentration of NO2 doubled, raised to some power, we don't know, is got to be equal to whatever happened to the rate. So look at the rate. What happened between experiment 1 and 2? It went from 1.35 to 2.7. Sounds to me like the rate doubled. So all you have to do is ask yourself, 2 to what power is equal to 2? And it turns out that question mark is equal to 1. So we can go ahead and come in here and fill in a 1. So we know it is first order with respect to nitrite ion, NO2. Let's see if we can do the same thing for the NH4. So you need to find 2 experiments where the NO2 is the same and yet the NH4 changes. And once again, you were right. Experiments 2 and 3 show that NO2 stays the same, but NH4 doubles. Let's go back to our handy dandy trick that we had before. When the amount of NH4 doubles, 2 raised to some power, we don't know what it is equal to, let's see what happened to the rate. So if you look over on the right-hand side, it went from 2.7 to 5.4. That means the rate doubled. So 2 to what power, we don't know, is equal to 2? Well, 2 to the power of 1. So our exponent here is 1. That's all you have to do. So we know that the rate law is rate is equal to K times ammonium raised to the first power times nitrite raised to the first power. Make sure you have that down in your notes because I'm about to have you do something else. Now that we have a rate law from before, see if you can find K. Take any of the experiments, it doesn't matter which one, find a value of K because you know a concentration for each one and you know a rate. See if you can find the K. We want y'all to sound smart when you talk about kinetics. So we can also talk about what is the overall reaction order. That last one we did, well, it was ammonium was first order because it had an exponent of 1. The NO2, nitrite, it was first order with respect to nitrite. So all you have to do is add them up. So that last equation we just did, yeah, it'd be second order overall. So let me give you a toughie. Here's a rate law. What order is this reaction overall? All you have to do is add up the exponents. 1 plus 2 plus 3 is 6. You would say a 6th order overall.